Okay, so today we're just going to continue with the list-based data structures that we were developing. We left off with recognizing that if you have my integer array list and my string array list here, that they're exactly the same thing, except that every instance of int has been changed into a string. So let's go ahead and generalize this by creating a third or a new copy of this. And instead I'm just going to call it my array list. And again, I'm only calling these things my because to distinguish them from the ones that are built into Java. Yep, there we go. All right. So the only difference that I'm going to do here is I'm going to make sure that it's parameterized, just like you did in Lab 6 when we covered object-oriented programming. That this class will be parameterized to hold any type T. Right? It could be a string, it could be a double, it could be whatever. It could be an invoice. Right? And all we're going to do is go through the same thing that we did on Wednesday, changing every instance of int. Instead of changing it into a string, we're going to change it into T. Right? There. Now, that's not going to work. We're going to come back and address that. But let's go ahead and take care of everything else. Integer here, when you add an element, you're not adding an element of an integer. You're adding a T, whatever that happens to be. T. Right? And what else? When we retrieve an element here, we're going to return an element of type T. Get size doesn't change. Replace element, instead of taking an integer and returning an integer, we're going to retake and return an element of type T. Likewise, we can parameterize that local variable there, temp, where we grab it to save it off so that we can return it later after we've replaced it. We're returning an element of type T there as well, temp. Otherwise, nothing else changes. And now I've solved this problem for any possible type in the future. You could hold invoices, you could hold people, you could hold stores in this, et cetera, et cetera. Right? And all it took was one piece of generic programming. Now this is a problem here. If this were an integer array, how many bytes would it take? The compiler needs to know this in order to allocate memory for it. So 10 integers, 4 bytes each, that's going to be 40 bytes. How many bytes for a double array? The name suggests it. Double, 8 each, so 80 total, right? What about this, though? T. How many bytes does the T take? No idea. The compiler doesn't know. That's why it's complaining about this. Right? So what we're going to have to do is we're going to have to use raw types. We're going to have to go back to the very beginning of Java where we didn't have parameterizations, we just had generic objects because everything in Java is a single table, and it's a single root inheritance hierarchy. Everything is an object. That's still not enough because array up here is an object. Now, if one way that I could solve this is by changing it into an object array. That breaks a whole bunch of other stuff down here, though, right? So I don't want to do that. I do want correct parameterization. So what I'm going to do is I'm going to force this to become an array of T's using explicit typecasting. It's still warning me here, right? Why is there a type safety check here? Remember that not golden, but do you remember that triangle, right? When you can take a subtype and treat it like a supertype, that's covariance, always safe. If you take a supertype and treat it like a subtype, that's sometimes safe. That's contravariance. And that's the sometimes here. It's giving you a warning. This may or may not be safe. Right? Be careful. The other one is invariance, right? Where you cannot force an ostrich to become a robin or vice versa. That's never safe. Why is it safe in this instance? It's because I've parameterized the class here, and I've made sure that the interface, the publicly facing interface, that you would not be able to add something in here that is not of type T. Right? Let me show you over here in demo. Let me try. I'm going to go ahead and erase this, my array list, and I'm going to make it into an integer, parameterize it into an integer. There we go. And let's go ahead and get rid of this second parameterization. No code changes at all, right? Because of my use of a parameterization, right? Would I be able to add, say, numbers.add element hello? Huh? No, why? because the interface prevents that. It must be an element of type t. It was parameterized with t being integer, and so string is not an integer. Invariant, I can detect that. I'm the compiler now. I can detect that as a compiler and give you a compiler error here. Right? So it is perfectly okay, despite this warning here, get rid of that. Despite this warning here, it is perfectly okay to force a contravariance. We don't have to use instance of to check. Why? Because the interface basically does that for us. It prevents anybody from putting something into this collection that should not be there. Now, that's not always true. Of course, you can go back to really old school Java and get rid of all parameterizations. Now the warning's out here instead of inside the class. Now we can do stuff like that. All right, oops, this would end up being, let me go ahead and get rid of this stuff. But I can go ahead and say numbers.add hello. I can do it. Right? Why? Because I've taken away the parameterizations. I've gone back in time to 1999 when Java didn't have parameterizations and polymorphism. All right, undo that, undo that, undo that. I don't want to live in 1999. I don't want to live in 2023 either, but I don't know what the perfect time would be. Probably like 300 years in the future where, you know, that's time, that's progression, right? Every single person, even the poorest of the poor, lives like kings basically in the year 2000 compared to like medieval times, right? When you died of dysentery at 3, right? But anyway, or I guess that was the Oregon Trail, right? They still play the Oregon Trail? Right? Okay. All right, so let me open up this demo and get rid of everything. That's basically all I want to do as far as this development here goes. So let's go ahead and now do a different type of testing. I'm going to do what's called a load test. I'm going to try to see how efficient my data structure is. I didn't want to get rid of everything. Let's go ahead and retain numbers there and retain this loop. But instead of starting at 10 and going up by 10s, we'll go ahead and go up to n and go up by 1s there. And I'll add the element, add the element, add the element. I'm not going to print it out because I don't want to see 1,000 elements here. What I want to do is I want to time and see how efficient my data structure is. So I'll go ahead and get the start time, which is you can do with system.currentTime in milliseconds. And then I'm going to go ahead and get the end time with the current time in milliseconds. And then I'm going to print that out. System.out.println, done. And it took %f seconds and the line. I need printf, sorry. And the end time minus the start time divided by 1,000. That's how long it took me in terms of seconds. There we go. Blazingly fast, right? 1/1000th of a second. It's probably barely even, you know, registerable. Okay. Let's kick this up to 10,000. Now, before I run this, predict. If it's 10 times as big, then you would expect it to be 10 times as slow, right? So that would be like 0.01 seconds. Okay, about that. Right? That 5 there is just a measuring inaccuracy, right? If I went up to 100,000, 10 times slower, right? 10 times slower now would be 0.15 seconds, or thereabout. We're getting up there now, right? But it's still comparable. It's still almost what we were expecting. Right? Let's kick that down and do something else with it now. Numbers.add element at index. And I'm going to add the element I to index 0. The previous demo that I just ran, that was adding it to the end, to the end, to the end, to the end, to the end. Now what I'm doing is I'm adding it to the beginning and shifting things down. Beginning, shifting things down, add it to the beginning. Shifting things down, adding it to the beginning. Do we remember what the time was for 1,000? I think it was like a 1,000th of a second. It's almost 50 times slower. Huh? We went up to a 10,000. What was it before? Something like that. Right. Oh, wow. It's almost 30 times slower now. Right. Let's go up by another factor of 10 here. So if we followed the same behavior as before, and it's 10 times as big, 10 times as slow, I would still only expect this to be, 1.5 seconds. Let's run it. Don't worry, it will run. Is this tolerable at all? 100,000 things? No. So it's almost 100 times slower. Not 10 times slower being 10 times bigger. It's 100 times slower. Right? Why? Here's a little bit of a preview of math. It's going to be n squared behavior. Right? So think about this. If I start with, whatever. There we go. I don't know what I was using. Weird. Oh, I was probably using a highlighter. Let's use n squared there. All right, so if it took, say, time t for something that was of size n, and we went up to 10n, right? In other words, we went from 1,000 to 10,000, 10,000 to 100,000, 100,000 to 1,000,000. I'm not even going to bother running that, but we will predict it. And if it took time t before, right, say 2 seconds, or it was 2 seconds here, and this is the behavior right here, then what would I expect here? Let's go ahead and plug this into this equation right here. 10n squared. Just a little bit of algebra here. What happens to the 10 there? 100 n squared. So if it was n squared before, now it's 100 n squared. In other words, 2 seconds becomes 200 seconds. All right. I can almost guarantee, let's go ahead and just try running it in the background there. Right? Instead of 15 seconds, it's going to be what? 100 times 15 is what? 1,500, right? How many minutes is that? A lot. I think it's going to be like 30 minutes or so. We'll just let that run. Right. All right. So in other words, it's bad. Right? Is there a better solution? And the better solution that I'm going to introduce to you is an alternative to array-based lists, which are called linked lists. Right? There's no underlying array. Instead, each node is stored in, a node. Here, I'll just copy all this over because we're going to visualize it. Instead, each element is stored inside of an individual node. That node has a reference to the element that you put into it, but also it has a pointer or a reference to another node. Therefore, they are linked or chained together. That's why we call it a linked list instead of an array list. Each basic operation involves traversing the list. Let's take a look at what that might look like. Here is a typical node. It holds an element. This is a reference to another node. And the way that we're going to visualize that is simply just a pointer. Okay? And Java doesn't have pointers, but it does have references, which are basically pointers that you can't do anything with. Right? There's the next node. Right? That one has a reference to the next node. 30. And I'll add one more here. 40. What about at the end? I'm going to use some Greek. What Greek letter is that? Phi, right? Phi is going to be our placeholder for nothing, right? Phi, phi, fo, fum, whatever, right? Now, in Java, we don't have phi. We don't have phi. What do we have that means nothing? Null. So I'm going to put a null, but eventually that's going to be null is going to be our placeholder there. That's not all languages. Python doesn't have null. What does it have? Do you remember? It's been so long. It's been like 4 weeks, 5 weeks. None, exactly. Right? All right. So this is why I'm using this placeholder here, this phi, because not all languages have null. Some languages have null. See? Some languages you would use what's called a sentinel node. You would have this thing that is stored in memory that indicates, no, this is the end of the list. So this is the beginning of the list, which we call the head. This is the end of the list, which we call the tail. Right? So it's like a snake. There's the head of the list and then the tail. If you need to access something, you always start at the head. There's the first node. That's not what we're looking for. If you're searching for this, I want to search for 40. You would need to traverse. Going from one node to the next node is called traversal. Going to the next node is traversal, 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 until you get to the end. Right? When you've fallen off the end of the list, that's it. Right? Can you work backwards? Not with the way that I've written this. But you could redesign it so that you could go forwards and backwards. That's called a doubly linked list, which we'll talk about later. Right? Otherwise, this is a pretty good start. I want to implement this in Java, and then we'll talk about the basic algorithm surrounding it. Okay? The first thing I'm going to need is this thing right here, a node. I'm going to go ahead and create a node class. New node. And I'm going to learn from my mistake previously, and I'm going to immediately parameterize this because I don't want to go back and change it and I realize, okay, now I need to parameterize this. This is going to be a node that can hold any type. I need two things, right? I need the element and the reference to the next node. So private t element. Right. Now, how do I do the node next? I'll call it next because that's what it is. But what's its type? Is it a integer? Nope. Is it a double? Nope. The next reference is a what? A node. And yes, you can do this. This is not recursion. Right? This is just basic composition. It's composition where this node owns an instance of another node. It's not owning an instance of itself. You could do that. You could do something eventually like, say, next is equal to this, right? And then then what does that look like visually over? That is recursion, basically. Where here, let me draw it. Where you've got a node, and then its next is referring to itself, right? But I'm not going to do that. Weird. Right? Let's make a constructor so we can actually create these things. Public node, and I'll take an element t of type t. This dot element is equal to element. Why am I not taking the next node immediately? I'm going to want to be able to create nodes without necessarily knowing where they're pointing. So I want to be able to create a node, put say 42 in it, but then have a question mark over here. Or better yet, phi, or better yet, because it's in Java, null. So this dot next is equal to null. Probably want some getters and maybe a setter, I don't know. Let's go ahead and generate some code here. I'm going to go ahead and generate all of them, select all, and then we'll think about it, okay? So obviously you're going to want to get the element because if you put something into a node with no way of getting it out, it kind of defeats the purpose. Do we want a setter though? Once you put this into the node, that represents that thing. You might want to change what it points to because you're going to want to change the configuration of the list, but do you want to change what's inside that node? Maybe, maybe not. Until we have a very good reason to do so, I'm going to say no and make it final. Get node. You're probably going to want to, again, traverse this list. So if you're at a node, you're certainly going to want to be able to get the next node so that you can go over to it. Right? Are you going to want to set the node? Yeah, because if you're not giving me a way to initialize next up here, I want a way to at least reset it later on. So now I have a very good reason not to make this final, right? And remember, your very good reasons need to be very good reasons, right? All capitalization on all of those, right? Not just a somewhat okay reason. Right? That's good for now. We're probably going to want to come back and rethink and add stuff to it, some bells and whistles. Let's go ahead and create a my linked list. And once again, I'm going to learn from my lesson and immediately parameterize it. Okay? How do we represent this linked list? Should I have a private collection of nodes? So node, what would it be? Node T's, there we go. Array of nodes. I could do that. What do I have then? I have each one of these stored in an array, and I'm back at square one. I don't want to keep track of all of them. Which one is the most important to keep track of? This one in the middle? How can you ever get to anything else? Likewise, this one at the end? How can you ever get to anything else? So what's the most important node here to keep track of? The head. So a list is nothing more than a single node that references the head, and that's it. I'm not going to keep track of everything else because that's an array list, and we've already seen that at least in one instance that was bad, right? Bad performance. Can we improve it with this? Okay. Public my linked list. What are we going to initialize head to here? Well, we started out with a visualization with 4 elements, right? Does this look like an empty list to you? Well, what's in there? I don't know. Do we need a node to represent an empty list? Remember before, we said that the end of the list is represented by phi, or in Java terms, null. So what does the empty list look like with respect to Java? Null. Right. Okay, we're probably going to want some basics. In fact, I'm going to take inspiration from my array list over here and say, yeah, I'm going to want to add an element. Yeah, I'm going to want to add an element at an index. Yeah, I'm going to want things like get size, et cetera, et cetera. Right. In fact, I'm going to want all of these things. So let's rethink this entirely. I want all of this stuff. I'm going to cut and paste it and modify it. Before I do that, let's revisit why we're doing this. We're going to leverage OOP principles. We've already seen good encapsulation. All the details of the class are contained inside the class. It takes care of handling all the low-level stuff of shrinking and growing and whatever else, and error checking and all that stuff. We've got good abstraction that we're only publishing how to use the list, how to interact with it, not how it works. We've got good polymorphism as of today with our parameterization. What do we not have here? What's the 4th pillar? Inheritance. So now let's leverage inheritance here. What I'm going to do, and I'm going to cut and paste everything from before and get rid of all the actual implementations. There we go. Get rid of that. Get rid of the implementation. In fact, do I need to change any of my documentation? Nope, I kept it as general as possible. Replaces the element. Did I say replaces the integer element? Replaces the string element? Nope. Kept it simple. Oh, that's private, so useless. Add element at index. Add the element at the end. There's my interface. Now I can come back to my original array list and say that I implement my list of elements of type T. Create interface. What's wrong with it? Public interface. Oh. Oopsie. Fat fingered. There we go. Let's go ahead and rename file to the correct spelling there. There we go. There. Now it's happy. But I'm also going to do the same thing over in my linked list because that's all the behavior that I want. Not only that, but it'll generate it for me. it'll only generate the actual methods, not the implementations, right? It's not that smart, right? Okay, I've got a lot of work ahead of me here. How do I do each one of these implementations in terms of this single node here, this head? What about get size? Let's start with the easy stuff. Let's come back over here to this example. The size here is what? 4. How would you go about computing that? Start with a counter. My hand will be a counter, 0. Start where? Well, the only place that you can start at the head. This is not null, so 1. Traverse to the next one. This is not null, so 2. Traverse to the next one. This is not null, so 3. This is not null. Traverse to the next one. 4. Traverse to the next one. We're done. Right. What kind of a loop does that suggest? A for loop or a while loop? While. Why? Do you know up front how many iterations you're going to go? If you did, you're done. Right? So while some condition. Okay. I'm going to have a counter here that I'll initialize to 0 because that's what I did with my fingers. Return that counter eventually. Right. Now, I need to say that while the current node is not null, then increment your counter and traverse to the next node. Help me fill in the blanks. I need a starting point because it's a while loop. I need an initialization before the while loop, right? Start at where? The head. So let's create a node here. Same parameterization, called current. Right? The current node that I'm currently looking at. In terms of this picture here, I've got this reference that I initially start out at the head. Then as I move along, what am I doing? I'm going to the next. Oops. I'm going to the next one. I'm going to the next one. I'm going to the next one. I'm going to update this current node right here. Current. Oops. Current. Okay. So, initialize it to this dot head. While current is not equal to null, in other words, I'm not at the end of the list, increment my counter, because this obviously is a node containing an element, counter plus plus. Traverse to the next node. How do I do that? Well, how can I get the next node? That getter that I wrote before, right? Get node. What do I do with it? Put it back into current. So the current is currently pointing to this node right here. Here's my current. Here's the node. I get the next node that it's connected to, and I've run out of hands. And then I update this to point to that next node. Let's see if it works. I'm going to kick this down. And I'm going to actually get rid of all this. We'll come back to it later, see if it does any better. Numbers.get size. Obviously, I do not have anything in there, so what should you expect here? Println numbers.get size. 0, it works. Done. Ship it. We'll come back to it. Maybe it does, maybe it doesn't. Let me get too many tabs. Let's come back over here. All right, maybe that works. To really test it, we're going to have to get something in there. All right, get element. What do we want to do first? Got plenty of time to do something. Add element. Remember that this is adding it to the end. So let's think about that. What if we have this list right here? And you want to add it to the end. First of all, can you immediately jump to the end like we did with an array-based list and then just put it there? Nope. The only thing that you have access to is the head. So let's go ahead and go here. Traverse, 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 traverse. Will we, if I've fallen off the end of the list, can I do anything with phi? Can I do anything with null? Nope. I want to stop here, right? So that what I can do is then create a brand new node to insert 42, erase this reference, and make it point to 42. And obviously 42 will be pointing to null as well. There, I've added it to the end. How do we take care of that over here? First of all, are there any index checking? No, because there's no index. Let's go ahead and create a new node first, because that's easy. Right? New node. Right? In fact, I'm going to call it what it is, new tail, right? Is equal to new node containing x. Right? So create new node. Right? Now what I'm going to do is I'm going to traverse to just before the end of the list. Right? In other words, get the last node. Okay? So same basic idea as down here. I'm going to have a current node that I initialized to the head. Right? Now, I'm going to have another while loop here. While you are not at the end of the list. In your demo class, you were still using the, oh yeah, that's a good point, thank you. Sorry, thank you. My array list, my list, and then this is going to be a linked list here. There. So still, should be 0. Yep, we're still good. Thank you. Thank you, online person. Whoever you are. Nobody uses their real name online. Bugs the hell out of me on Discord. Because I need to talk to you. Who are you? That's why I'm Seabrook on Discord. Okay. How do I know that I'm not at the end of the list? Not is the current node null, but what? The current's next node is null. That's how I know that I'm at the end of the list. While current.getNext is not equal to null. That's very verbose there, right? I'm going to update current is equal to current.getNext. Right? Once I'm done, we'll worry about refactoring that because it does work here. What we're going to do now is we're going to do what I did in the picture. I've got access to this node and the old tail, and I've got access to this node, the new tail. I'm simply going to make the old tail point to the new tail here. And I've got a setter to do that. Right? Current.setNext to the new tail. There. Okay. Now before we test this, let's think about this verbose statement here. While the next one is not null. What's another way of saying this? Here's the current node. While the current one has a next node. That sounds like a lot better in English at least, right? Well, let's make our code look more like that English. Where does that belong? Hey, current, your node, do you have another next? I'm asking that question to what class? The node class. So it probably belongs in the node class. Public Boolean has next. How do you know if you have a next if you're a node? If this dot next is equal to null, I will return false. No, I don't have a next. Else, return true. Switch those around. Not null, true, and false. A little bit better. Can we get it down to one line? Code golf. Return what? If this is true, return true. If it's false, return false. So just return it. There we go. Now over here in my linked list, I can say, while the current node has next. Go to it. Let's test it. Demo. Let me go ahead and put in 3 things. Numbers dot add 10, 20, 30. How big should it be? 3. sunk. Cannot invoke has next because current is null. Huh? Okay. That happened in add element line 19. Okay. Let's understand what's going on here by setting a breakpoint and taking a look around. Switch to my debug perspective here. Okay. I'm about to add 10. This works perfectly fine. I'm going to step into that function and see what's going on. Okay, I don't care about that. Nope, we haven't had a problem yet. There we go. All right, so add element. There's x, the element that we're about to add, 10. There's my new tail. If I expand this out, you see, in fact, that the next is null and the value is 10. The element is 10. The current has been initialized to head, but what about this class right here? What is the head? It's null. So what is current? It's also null. Can you invoke a hasNext method on the null thing? Nope. There's our problem. We got stuck before we even inserted the first element. As with a lot of things, you have to think about corner cases, edge cases, special cases. So what special case do we need to think about here? What if the list is empty? You don't have a head to start out and traverse to the end. So what should we do? If this dot head is null, we should handle that separately. This dot head is equal to our new tail. So I'm going to move this up here. New tail. Right. I'm done at that point. What should I do to make sure that I don't execute the rest of this? Return. Right. Let's see if that fixed it, at least for that 10. Oh, okay. Maybe it fixed it for all three. Right? Because remember, we're adding 10, 20, and 30. How do I know? I could run I could run the debugger and switch this. Let's go ahead and step over that, step over that, step over that, step over that. Let's take a look at what numbers looks like right now. There's the head with element 10 in it. It's pointing to next, which is another element, 20, which is pointing to next element 30, and that's at the end of the list. Hey, look at there. There's your visualization of a linked list right there in the debugger. One node points to the next node, points to the next node, points to the next node. Right. Looks all good to me. Let's go ahead and stop this, go back to the Java perspective. But that's got me thinking. What if, or get rid of the node class for now, what if I added a million things to it? How complex would this get size thing be? I don't want that. I want get size down here. If I have a million things in there, you have to start at the head and count to 1,000,000. If I have 1,000,000,000 things in there, you have to start at the head and count to 1,000,000,000. Is there a better way? If we put something in, if there were 5 things in there before and we put something in new, how many things are there now? 6, right? Why don't you just keep track of that? I'm going to refactor this a little bit. Public, or not public, private, int size. Just like we did with an array-based list. When we add an element, we go ahead and increment. This dot size plus plus if we do it as the head, otherwise this dot size after we add it down here. If you want to, you can go ahead and do it up here instead and not have that repeated code, but I like to be explicit like this. Now we don't have to do this loop at all. What do we do in get size? Return this dot size. No counting to 1,000,000, no counting to 1,000,000,000. You keep track of it as you go along. Little bit more work to make sure that anytime we add an element, we need to add one. Anytime we remove an element, we need to subtract one, but it's going to be way more efficient. Okay? Regression test. Make sure nothing broke. But you know what? I erased all that stuff, didn't I? Let's undo, undo, undo. Because that seems like a really nifty loop to do something else. Right, oops. This dot size plus plus. Let's go ahead and grab this. Right, and return this dot size. I want a toString method because I don't want to be looking at my debugger all the time. Public string toString. That was a really nice loop that worked really, really well. Right? Instead of a counter, let's go ahead and create a string builder. SB is equal to new string builder. And I'm going to emulate what we did with the array list. SB.append, at the beginning, a square bracket with a space. And then, for each element, instead of incrementing my counter here, what I'll do is I'll append whatever's in there. SB.append current.getElement. SB.append a comma space. And then traverse to the next element until we're down and done. SB.toString. Let's test that. Actually, I'm just going to get rid of this. We'll know how big it is when we see it. 10, 20, 30. Ah, what did I forget at the end? SB.append, that nice closing square bracket. In another section, we had a discussion on what we should call this. I've always called it the coding Oxford comma, right? Cake, ice cream, and candy. Do you put that last comma there or not? That's called the Oxford comma, right? This is the Oxford comma in coding because do you need it? No, but do you want it? Do you want to write code to make sure that you don't put it in there? Help me. How could we change this code so that we're not putting in that coding Oxford comma? Stop short, right? Current dot has next. Then you do it, and then at the end, what is current dot, or sorry, SB.append current dot get element. But instead of doing the Oxford comma there, you get rid of it. Cool. That obsession to get rid of that little comma though, did it break anything else? Let's find out. What if you print it when it's empty? What if you print it when there's only one thing in there? What if you print it when there's two things in there? What if you print it when there are three things in there? Let's make sure that we didn't break anything. We did. So in the last 5 minutes here, help me fix this. What did we do here? If it was an empty list, that was a corner case, a special case, an edge case. Might there be an edge case here? If it's empty, what should we return? Thing that we did on the array-based list was something that looked like this. Right? Run it again, see if it works. Empty, 10, 20, 30, 10, 20, 30, 10, 20, 30. Right? I like that. Right? This is good, rigorous testing. Testing all possibilities. You go and change something, you have to rewrite all these tests, right? Because I'm going to get rid of them now, right? Okay, it worked. Get rid of that, get rid of that, get rid of that. Again, a motivation for writing proper unit tests, because then you can just run it, right? Run it every single time. It's just like we've taken that work away from you, right? Because that's how we want to grade for all the labs, but that's what you would do in real life. Right? Believe me, I don't like writing test cases either. All right, that's good. Let's preview the rest of this stuff. Add element, that adds it to the end. What about add element at index? What's that going to look like at least? What if you wanted to add the element to between right here? First of all, you've got to get there, right? You'll traverse here, traverse here, traverse here, and realize maybe I want both of these nodes. Because if I want to insert something, what do I need to do? 42, trapezoid instead. and erase this link right here. And make that point to that, and make that point to that. Pull it like a link, a chain link, and now you've inserted it at that location. What if we wanted to replace something? Same basic operation that I'm eventually going to have to find that node. If I'm going to do anything index-based, it's going to involve, as a first step, finding that node or finding that other node. Maybe I can simplify a lot of this by writing that function first. Right? In fact, 4 minutes, forget it. You've got stuff to do. It's a weekend. We'll save that for Monday. All right, yep, thanks again for the comment. Otherwise, have a good weekend.